Assalamu alaikum. Hello, grade 11 GED 2019-2020 students. We are still in topic 4, electric fields. This is lesson 4.2 as mentioned in your syllabus, concepts of electric field and electric field strength, and this is part 1. Here we are going to define electric field and electric field strength. We'll represent the electric field by field lines, calculating the electric field strength due to a point charge. Let's start. Electric field. What is electric field? And here we will read here. An electric field is a region of space where electric charge experience a force. So it means there should be a charge and a region around this charge, and the electric charge experience a force at any point here. Okay, that field is called electric field, where the force due to electric charge occurs. Now, electric fields act on objects with electric charge. Whenever there is electric charge, there will be electric field, a space around it. As you saw before, magnetic field, or you are going to see, inshallah, magnetic fields act on magnetic materials or moving charges, and gravitational fields act on objects with mass. Let's go with how to represent the electric field. Electric field can be represented by lines. We call them electric field lines. So they are not real lines, just for representing the electric field. They have many characteristics. The line starts on a positive charge and end on a negative charge. You see here, you have a positive charge and a negative charge. The line goes from the positive to the negative. So it's always out of the positive. Here also, from the positive towards the negative. The lines never touch or cross. As you see here, in all these figures, the lines does not touch or cross each other, because they only have a certain direction at each point. The strength of the electric field is indicated by the closeness of the lines. What does this mean? That as the lines are closer to each other, the stronger the field is. This means here the lines, for example, near to this charge, closer to each other. So the field is stronger. As we get farther from the charge, they are separated from each other with some distances, going farther and farther. So the field strength is less. Also here, for example here, as we go farther away from the charge, the separation will increase. So it means the field is coming weaker. Here, the lines are closer to each other. So, more strong electric field we have here. It's very important to know here, for example, and we are going to come to this point for the few next lessons. If the electric field lines are parallel, this means here in this region, this means we have a constant electric field. It means, for example, at this point, the field has the same value and the same direction here, directing from positive to negative. Here, at any point here in this region, it has the same value and the same direction. So this means we have a uniform electric field that can be represented by parallel lines where they have the same direction and the field has the same direction and the same value at any point. But here you can see here, okay, at this point the direction is different from this point. And of course, farther we are going from the charge, as we mentioned, the weaker the field is becoming. So also the electric field has different directions and different values at any point. Here also, okay, for example, we are getting curves here, not straight lines. That means the value for the field is changing. For this, for example, point, we have to draw a tangent to this point that gives us the direction of the field. Here, this is the direction of the field. Here, this is the direction of the field. So for any curved line, okay, the direction of the field is the tangent at that point. And of course, we are having also different values for electric field here. Okay. Now, here we have which of the three field diagrams represents two positive charge repelling in each other and two negative charge and two opposite charge. For a positive charge, we should know that the fields are going outside the charge, as we saw before. For a negative charge, because it's going from positive to negative, so for a negative charge, the field lines are going towards inside the charge. We call this radial field. It seems to be, the field lines seems to be radiated from the center here. Okay, now here we have lines repelling each other. Yes? So of course these both should be similar charges. No any line between them. So there is a repulsion. But what type of charge they are? Lines are going outside here, so it means that this is positive, and also this is positive. Here there are lines going from a charge to the other. And we know that they should be directed from positive to negative. Yes? Coming from the positive going toward negative. So this should be positive, this should be negative. Again, these are two similar charges, and lines are going toward the inside the charge. So they should be negative and a negative. Okay. Electric field strength. What we mean by electric field strength now? It's a very important definition for our lesson for today. The electric field strength at point is the force per unit charge that acts on a small stationary positive charge at that point. Suppose we have for example, electric field here due to this charge or this charged conductor. We have electric field. And if there is a small point charge here, which is Q, very small and stationary charge, this will be affected by the electric field. We said that this electric field will affect by a force, which is electric force, at any point in this field. So if there is a point charge, small stationary positive charge Q in this field, it will be affected by this force. Which force? That is caused by the electric field. So the strength, electric field strength E, electric field strength E at this point is the force per unit charge of this stationary positive charge. So dividing force, again, which force? That has been caused by electric field. Okay, so force divided by this charge will give the electric field strength at this point. Our force is in Newton, our charge is Coulomb, so electric field strength will be Newton per Coulomb. This is the SI unit for electric field strength. Again, electric field strength, so for simplicity we call it field strength, or electric field is equal to force divided by charge, this charge. That will give us the electric field strength at this point. Now let's do an example. Calculate the electric force on a point charge of 4 times 10 to the minus 10 Coulomb. If the charge is placed at an electric field so we have an electric field which is equal to 500 newtons per Coulomb. In this field, a charge has been placed. What is the charge? Force times 10 to the minus 10 Coulomb. They are asking to calculate the electric field, the electric force. From the definition here, E equal to F divided by Q, so our F equal to E times Q, which E, this is our E, 500, okay, it's Newton per Coulomb. times the charge, okay, that we are asked to calculate the force on it, which is 4 times 10 to the minus 10 coulomb. Column will cancel with column, so we will end with a force in the unit of Newton. Okay, so how we are going to get 5,000 times 10 times 10 to the minus 10. It will give us 2 times 10 to the minus 7 Newton. This is the force. Okay, now the electric field strength due to a point charge. Now, suppose we have a point charge here, which is Q1, and there is electric field around this charge. Okay, if we had another test charge here, it should be straight line. If we have a test charge here, for example, a small stationary test charge, which is Q2, and we want to calculate the electric field strength E due to this point charge. If the separation, now let's avoid clearly, and this is our small stationary test charge Q2. If the separation between Q2 and the center of Q1 is, for example, R, now we know that as we mentioned before, E, the electric field strength, equal to force by this charge. We are trying now here to calculate the electric field strength at this charge. So it should be F, the electric force caused by this charge, divided by this testing charge. Yes? Okay. Now we know that there is an interaction force between these two from the previous lesson, which is equal to K Q1, yes, Q2 over the square of the distance between them. Okay, let's substitute F in equation 1. Substitute F from 2 F from equation 2 in equation 1. So we will have E equal to, let's put our F here, K Q1 Q2 over R square, and already we have here a Q2. So this will cancel with this. We will end with K Q1 over R square, and this will give us the electric field strength to this point charge Q1. You have to be very careful here. We are calculating the electric field strength due to a point charge. Where is the point charge that causing the electric field? This Q1. So it is equal to K Q1 over R square. So in general, if we have any Q, we will get KQ over R square. Q is the charge which is causing the electric field, and R is the distance between the point charge Q and the point at which we are calculating E. So if we are calculating E at this point, so R is from the point till here, the charge which is causing the electric field. Okay, now again this K, as you know before, it's 1 over 4 pi epsilon naught. This is the permittivity for free space, but we know the value of K, so just we have to substitute with the value of K. Now, in example, a small sphere carries a charge of, okay, so we have a spherical conductor that carries a charge of 2.4 times 10 to the minus 9 coulomb. And we are dealing with this sphere as a point charge, that the charge is concentrated here at the center. Calculate the electric field strength at a distance of, we have different distances. Before going to these calculations, now we have E equal to KQ over R square. So it is very clear for you here that E is directly proportional to Q, and it is inversely proportional with R square. That means if R is increasing, E will decrease, as we have seen before for the force. Now, a small, calculate the electric field strength at a distance of 2 centimeters. So we have a point here which is 2 centimeters away from the center. This is the center, the point 2 centimeters away from the center. We want to calculate the electric field strength here at this point. And then 4 centimeters. Of course, when, okay, let's just do part A. So we will get, applying our formula, K Q over R square. We will get what here? K 9 times 10 to the 9 constant. Our Q is 2.4. We should make sure that we are having the SI units. This is coulomb. This is centimeter, and this should be divided by 100, so 0.02 meters. Yes. So 2.4 times 10 to the minus 9. This is Q, and our R is 0.02 centimeters, 0.02 whole square, and this will give us 5.4 times 10 to the 4 Newton per coulomb. Before going to part B, to do the calculation for part B, 4 centimeters from the center. So what do you expect here? R is increasing. So what should happen? What will happen to E? Of course, it will decrease. But by how much factor it's going to decrease? Now, let's do that. E equal to, at part B, again, K, 9 times 10 to the 9. Our Q is the same Q, 2.4 10 to the minus 9. Our R now became 4 centimeter. The point is furthermore. So 4 divided by 100, it is 0.04 whole square. All should be in SI unit. The important thing here in physics, first, I think drawing diagram is very important. It will give you a whole picture about whatever you have to do. After drawing the figure, you go and see what is given and what is needed to be calculated. Then make sure about the units. So here SI unit, and this was in centimeter. We converted to meter. The same should be here for centimeter. Then you have to substitute. So it will give us here 1.35 times 10 to the 4 Newton per column. I think, as we expected, that it will decrease because the distance increased. But if you see here, the distance was doubled, increased by a factor of 2. So you can do that, part B, with another, for example, you prove that by another mathematics. Like here, E proportional to 1 over R square. So if we have our E1 and this is our R1, Q is constant. Q is constant. So E2 again will be proportional to R2 square. So the distance was changing, so also we will get E2 instead of E1. Yes? So if you are going, for example, here to divide E2 by E1, and we have E1, and we are calculating our E2 here in this case. Okay, now it should be 1 over R2 square divided by this 1 over R1 square. This should be equal to 1 over R2 square, and convert this division to multiplication and take the inverse of 1 over R1 square. It will be R1 square over 1. I think you are getting here R1 square over R2 square. So this is very important that our E2 over E1 equal to R1 square over R2 square. So if our R1 is, even if we are going to take it in centimeter, it doesn't make sense, because centimeter square will be cancelled with another centimeter square. So here for ratios, units are not important to be SI unit. The most important thing, you are dealing with the same unit, up and down. So our R1 was 2 square is 4, and our R2 was 4, and 4 square is 16. Our E2, I don't know what is our E2. Our E1, we got our E1. This is our E1. This is 5.4 times 10 to the 4. From here, one can get E2 equal to 4, this 4, times this, 5.4 times 10 to the 4, divide by 16, and this will give you the same value, 1.35 times 10 to the 4 Newton per column. and this was another method to find part B. Okay, I'm just showing you, this is the simplest way to do that. Just substitute by your new R. But we are trying to make a relationship between E and R. Once here, E proportional to, and you don't need to go through all these calculations. E proportional to 1 over R square. Yes? Yes. So, if here R was doubled, instead of 2, it's 4. So, if R is doubled, it will be 2R whole square. That will give us, is it clear? Again, I'm going to do that. Okay. If, let's go back to, okay, E proportional to R square. That one was E1. Our E2 should be proportional, this is R1, and this should be R2 whole square. And our R2 was double of R1. So it was, E2 was 1 over double of R1 whole square. This will give us 1 over 4 R1 square. This was 1 over R square. E2 will be proportional with 1 over 4 R square. 2 square is 4 and R1 square. So that means this is 1 over 4 R1 square. That means this is 1 over 1 R1 square, 4 R1 square. So E2 will increase, if R is increasing by a factor of 2, E2 will decrease. Okay, by which factor? 2 square is 4, so it will be increased, it will be decreased by the fourth.